Hello, my name is Terry Collins. Welcome to Lesson 1, Module 2, Sustainability Determinants in Green Chemistry. In this module, we'll explore green chemistry's relationship to the broader challenges of creating a sustainable future. We'll start by looking at how green chemistry fits into the big picture of sustainability. We will be emphasizing throughout the module and course that sustainability calls for long-term, cross-disciplinary thinking. To help us appreciate the big picture, we will define and discuss two classes of sustainability determinants, which control our civilization's course toward or away from sustainability: natural and human. And we will conclude this module by considering that green chemistry's role is to help orient the human determinants to pull the natural determinants towards sustainability. In today's world, public discourse on development focuses almost invariably on the economy: local, regional, national, global. That's because we worry, quite appropriately, about wealth generation and jobs to give more people a better life. But in this discussion, key elements for sustainability are often missing. The simple truth is that we do not cost account health and environmental negatives. But such cost accounting is vital for choosing among options for technological development to achieve sustainability. The economy is a subsystem of the Earth and its ecosphere, and not vice versa. So you can't build a sustainable economy that is as large as the current global one without adapting to ecospherical constraints. The economy depends for its existence on the massive daily acquisition of matter from the ecosphere, where it is transformed into usable products and processes. When the usefulness is exhausted, the spent matter is ejected back to the ecosphere as waste. While matter is in the economy circle, we can increase the efficiency of its use, and we can practice recycling. Our technological sustainability challenges are associated with these matter flows. We are expanding the economy on a global scale and greatly increasing the economy ecosphere matter flows at the same time. We are doing this predominantly under our model of maximizing profits, where the longer-term adverse impacts of matter flows on health and the environment are given little attention and no upfront value. Green chemistry can help at each level of this analysis. Green chemists can reduce hazardous matter before it even enters the economy. For example, lead batteries can be targeted for replacement by less hazardous alternatives and reduce lead mining in the process. Green chemists are inventing new ways for converting solar to electric or chemical energy. Solar energy is unique among energy sources because the feedstock is not terrestrial. It's hydrogen burning in nuclear fusion in the sun. So moving to solar energy reduces enormously both the intake and exit matter flows. Within the economy, green chemists can do many things. For example, we can work to replace everyday chemicals that are developmental disruptors with alternatives that are not. We'll consider such challenges extensively in later lessons. And at the exiting flows, new approaches for degrading toxic residuals in green ways will reduce contaminants of the water, air, and land. Green chemistry is a key part of our sustainability quest, but only a part. We must also adapt our dominant short-term economic thinking to rely more on the longer-term thinking that sustainability calls for. To see this, imagine the progress of the 21st century along this white timeline. Now consider that in this time, our civilization will either become more sustainable or it will become less sustainable. What will determine the sustainability trajectory? The concept of sustainability determinants can help us to understand how important the development of greener technologies can be when shaping the future. By looking at a broad sample of these determinants, green chemistry's centrality to the pursuit of sustainability will become clearer. There are two kinds of determinants, natural and human. We will list the natural determinants below the white timeline and shortly human determinants above it. Natural determinants include planetary systems, processes, and resources that operated or were in existence long before advanced technologies of any kind emerged. Feedstocks. Natural chemistry, the world's chemistry absent human influence. The climate and water are all examples of natural determinants. Notice that the feedstocks vector proceeds to 2075. As with each natural determinant, the vector length is a guess at the time when our civilization will be irreversibly damaged if we continue handling feedstocks according to current models. Obviously, the time lengths are subject to much debate. Now let's look at the human determinants. These can be considered as drivers that we control. They can be positive or negative with respect to sustainability. Research and business, for example, can advance unsustainable products and processes or sustainable ones. If the products are sustainable, they can move our civilization towards a future that we can literally live with. The same is true for all the human determinants. For human determinants, the length of the timeline vectors are guesses of how long it will take from the point that a sustainability-oriented activity, green chemistry education for example, has begun to the point that it starts reorienting a natural determinant, natural chemistry for example, in the direction of sustainability. From this analysis, you can clearly see the dangers of getting things wrong. If we do not develop green chemistry education to live up to its potential by, for example, allowing prevailing cultural features of the chemical enterprise to limit our dealing forthrightly with hazardous substances, then we will get the direction wrong. And that will contribute to an unfavorable reorientation of the natural determinants, even if the force comes from no more than the wasted opportunities that erroneous diversions will produce. Like a compass helps us locate true north, with sustainability, directionality in the human determinants is at the heart of things. But this is very optimistic. It means we can change the course of our civilization towards a more sustainable future by consciously transforming the way we operate the human determinants. It isn't easy, but it can be done if we have the will. So let's return now to the three grand technology challenges: safe energy, renewable feedstocks, and toxic substances. We have to reorient all the human determinants to enable us to move our economy ever more certainly towards solving these challenges. Green chemists aim to provide the technology tools we need, but the challenges are highly interdisciplinary and require collaborations among appropriate experts. Not only do we have to build appropriate scientific collaborations, but also politicians, businessmen, inventors, regulators, advocates, world leaders, and many other experts all have key roles to play in achieving success. The lecturers for this course are leaders in different fields who are doing their part right now. And so we have to continue working together to imagine what a sustainable future will look like and then pursue it, refining our plan as we go, but guided always by the need to choose shorter-term goals of economic development that are compatible with longer-term ambitions for building a sustainable world. So how can green chemistry education help? Well, quite simply by focusing chemistry education, research, and innovation on sustainability challenges. And to do this, green chemists must learn about hazards and prioritize them for reduction or elimination. We also have to learn how to design against hazards, which means we have to understand the hazards deeply. And we must also understand the cultural features that are barriers in the journey towards sustainability.